Ladies and gentlemen, it's really my pleasure and honor to be here as a moderator to present you and exploring together the boundaries of Uspace developments in the context of exploratory research projects. My name is Nila Gaçdiken. I am grateful to be the program manager of the exploratory research projects of the Uspace. And during these sessions, well, unfortunately, we cannot present you all our projects, exploratory research projects, but we have selected among them 7. And they will very briefly go through, introduce their developments. Most of them have either ended or almost about to end. They have worked very hard 2 years or 2 years and a half, depending on when they have started. And here I have the pleasure, to give the floor to them so that they can present their findings. But they will have only 7 minutes. So in that 7 minutes, obviously, for the hard work of 2 years and 2 years and a half, it's hard really to, put that all together. Therefore, I would like to also invite you to take the opportunity at the breaks to really zoom into particularly their demonstrations. They have very interesting stands, so please do not hesitate to visit their stand during the breaks. So, although they have worked individually on their corner, all of them have tried to answer a fundamental question. What is the best way? What is the most efficient way to use the Uspace capacity, but without undermining the safety? All have looked from their own angle, either through developing enabling technologies or developing new concepts, and that's where they come together. So now, I also would like to ask, ending their, presentations with another critical question. The question would be, now that you have worked in the exploratory research project, we know that they have low level of maturity. We only reached TRL2 in exploratory research. And we have also heard yesterday, how urgent the market is, and having in mind also the drone strategy 2.0. What would be the most urgent research and development topic that you would like to recommend for the next phase? So I would really appreciate in that 7 minutes you also try to answer that question. With that, I would like to start with Bubbles, but I have a difficulty to see Yuan around. Is he here? Yeah. I would like to invite Yuan, but before inviting him, let me say what Bubbles is. At least in our understanding, is SESAR. So it stands for defining the building basic blocks for Uspace separation management service. Looking into this fundamental question that I have mentioned before, Bubbles is looking from an angle, what would be the separation minima and who will be the separator? They have really worked on hard to answer that question, and they have even proposed an algorithm to get there. So that project will be presented by Yuan Vincent Balbort Tejador. He has a PhD in telecommunication and engineering from the Polytechnic University of Valencia in Spain. And since 1993, he has been in communications department and being a full professor since 2011. He has co-authored more than 130 papers and has been participating more than 100 research projects. So please welcome me, and you have the floor. Please take it, Yuan, and you have 7 minutes to present.
Well, thank you very much. Well, Bubbles is an exploratory research project, as Neil said. Has been executed by 5 partners coming from 4 countries. The project has been led by the Polytechnic University of Valencia, and the other partners were the University of Coimbra in Portugal, the University of La Sapienza in Rome. Eurocontrol was also one of our partners, and a well-known Spanish company, which is Indra. the main objective of Bubbles was to formulate and validate a concept of operations for providing separation management by means of the USpace. First, we tried to develop procedures to define separation minima and describe how these separation minima could be maintained and which are the performances we need to guarantee these separation minima are maintained. We also intended to validate this procedure by means of a combination of simulation and experimental flight tests. And finally, we aim at promoting the embracement, the public embracement of these technologies, basically by emphasizing the level of safety that could be attained by the USpace. The main result of Bubbles is the process we developed to obtain these separation minima and these performances. First, we start by defining a target level of safety. We conducted a thorough review of the accidents in manned aviation, and we tried to establish a comparison between what happened in manned aviation for more than 50 years and what can happen in the USpace. And finally, we established a target level of safety of 10 to the power of -6 fatalities per flight hour. And then we also, by analyzing the share of responsibilities in accidents in a historical review, we apportioned 2.5 to the power of -7 fatalities per flight hours to operational and human reasons that can be somehow mitigated by the USpace. Afterwards, we propose a classification of traffic in terms of operational risk. And we based this classification on the categories established by the European regulation: open, specific, certified, plus manned aviation. Once we have classified the traffic, we need to characterize the scenario. We have proposed a total of 9 reference scenarios where USpace operations can take place. And for instance, for a medium density of operation scenario in controlled airspace, we proposed, based on previous work published by colleagues through many years of research, basically in SESAR, a distribution of traffic among the different categories we have previously defined. And also define physically the scenario. In this case, we consider a 5 by 5 kilometer scenario with 3 flight layers. It's a structured airspace with 3 flight layers from 20 and 120 meters, and with an expected demand of 15 drones per layer. Considering this, and applying the risk model we developed, we identify the maximum meter collision frequency that can be accepted if we intend to comply with the target level of safety of 2.5 to the power of -7. With this, and by means of simulations, we develop, using a simulator, we have designed and implemented in the project, we identify that with a set of separation minima, depending on the traffic category, between 60 and 260 meters, and with tactical conflict thresholds between 165 meters and 820 meters, with these 3 vertical layers, we can achieve a frequency of meter collisions of 2 to the power of -6, which is compliant with the maximum value we had identified, and the capacity is around a bit higher than 17 drones per layer, which fits meets the requirement of the demand of 15 drones per layer. Afterwards, we express these results in terms of what we call actual level of safety, in terms of fatalities per year. In this case, with this configuration, we expect 1 fatality every 8 years. This is a figure much easier to understand to the public than any other way to express the target level of safety in other metrics that would be more usual in aeronautics. But in order to achieve these results, we need also to establish the risk ratios of the different mitigation barriers that exist between the takeoff and a possible middle collision, the strategic and the tactical collisions, and even if we consider that the collision avoidance barrier. And in order to achieve these risk ratios, we define a set of safety and performance requirements. These safety and performance requirements are performance-based, so we establish a set of performance metrics and develop a tool to assess the performance of the CNS system, basically communication and surveillance systems, in order to guarantee that the required performance is achieved. And if not, the process is restarted in order to determine the new separation minima and the new necessary risk ratios. We validated the concept by means of simulations and also by means of flight trials. We conducted flight tests involving 14 drones flying over these 5 by 5 square kilometers in an area in the north of Valencia. And well, we validated the concept beyond the TL2 V1 that was the original goal of the project, but there is still some work to be done before we can achieve the TL4 V2. And this is the contact information of the project. So feel free to contact us if you are interested in the project and want to learn more. Thank you very much.
Before you go on, one question for you. Yeah. Could you please respond? You know, you said we are only TRL2.
Yeah.
What do you think the most urged research and development topic from your perspective?
Well, to be honest, and having Pablo in front of me, we have jointly participated in a proposal for a fast-track project trying to promote the separation minimum computation and the demand and capacity balancing towards TRL7, because we think that in order to enable more complex operation in U3, U4 environment, the tactical and strategic management of capacity and separation and safety is a must. So I think, and sorry for answering on behalf of you, Pablo, but
I will ask you another question, don't worry. Thank you very much.
You're welcome.
And thanks for also respecting the time that you have been given. So thanks a lot again. So now this brings us to DACUS, but before I present you, just give me a minute. So now that we have the separation management service introduced, to see now how the capacity will be managed in the airspace. That's where the DACUS comes into the game. It refers to demand and capacity optimization in Uspace. As you know, that demand for drones over the populated areas would be exploding. There will be need, therefore, for a limiting number of drones to ensure the availability of the access, to adequately balance between system capacity and the demand, and as well as to have fair and prioritized access to this airspace. And that is the research topic that DACUS is addressing and defining the feature demand and capacity balancing. Well, I have another question there for you then, because Johan already addressed your question. The question would be, what could be the short-term implementation of dynamic capacity management? What other applications in short-term you see? With that, let me present Pablo Sanchez Ascanila. He is an aeronautical engineer working for CRIDA, Research and Development Center owned by ANAIR. He has more than 20 years experience in the ATM R&D and then drones and UTM domain. Since 2016, he has involved in diverse initiatives in the Uspace. Actually, when I talk to him, sometimes I really get lost because he knows so much that sometimes it's difficult to put into simple terms. So we can really feel his vast experience behind. And at the moment, he is the project manager of the DACUS and the coordinator of one of the solutions of AURA. Please welcome, and the floor is yours, Pablo.
Thank you very much for the introduction, Neil, and good morning to all of you. Well, I will talk right now about DACUS. And first, I will start by introducing the consortium. We are a wide consortium, 11 partners from 5 different countries. You can see they are key actors in the navigation today, in the aviation today, sorry. But apart from that, there are 2 additional partners that I should mention. We have Toulouse Metropole, a city in the consortium, and we have one company which is doing deliveries with drones today in Reykjavik, which is AHA. And what is the reason for this wide consortium? It is because we are addressing, as Neil has said, the demand and capacity management process. And well, this is the objective of DACUS. This advanced USpace services, which is named Dynamic Capacity Management in Urban Environments. And to design these services, it was necessary to face, for us, 4 key challenges. The first one is the notion of capacity. Well, everybody will know the notion of today with regards to ATM. You have sectors, you have controllers, and there is a maximum number of operations that can be managed in a sector in order to ensure that safety and separation is maintained. But okay, you have to think that USpace will be a fully automated system. There will be no human actors, and this will imply that the limits needs to be investigated in other direction. This is the first challenge. The second one is related to the social impact. This is something that was mentioned yesterday. This is something that was mentioned today by Robin. No? What about the social impact of the operations, especially in urban environments? So probably it is necessary to limit also the operation with regards to this idea of the social impact. And what else? Then we have the uncertainty of the demand. This is another challenge in USpace. You cannot imagine an operation. Imagine you need to have lunch. You request to have your lunch in half an hour. You cannot wait because USpace is not providing the necessary capacity or because the demand was not determined in advance. This is another challenge. And the last one is related to the mitigation measures. In ATM, you have the regulations, you can stay on ground, but probably we need to address this challenge in a different way, trying to ensure that drones are operating in free routing and only impose restrictions when they are needed. These were the key challenges of DACUS, and with these challenges, we designed several prototypes and we performed several experiments. The prototypes are, the first one, the collision risk prototype, that tries to identify the risk of collision first in the air and then the consequences on ground, the potential collisions on the citizens because of, well, as the consequence of a crash or a direct impact over the population. We try to measure through a collision risk model how the risk is distributed in the whole USpace airspace and well, to determine with a certain threshold what could be the imbalances, the areas where it is necessary to implement measures based on the risk. The other point is the social impact prototype. And here it was necessary to define new metrics, new indicators to measure this. The first one was related to the noise annoyance, noise disturbance. And let's take into account that this is not a matter only of measuring the noise itself, but also to know how the noise is impacting the population. So if there is no population, there is no noise. And apart from the noise, we have also the visual impact, how this set of operations in the skies could be impacting the people that are in the garden and so on, no? How this visual pollution is affecting to the population as a limiting factor. Then we went into the uncertainty of the demand, and we measured how the uncertainty could be impacting the determination of imbalances in this dynamic capacity management service. And I can anticipate that the imbalances, or let's say the uncertainties related to the departure time, to the contingencies that could happen, even to the weather, could be highly impacting this determination of imbalances. And well, finally, we integrated all these prototypes together and we performed one fast-time simulation in order to test the measures to be implemented in USpace. This was mainly the scope of the DACUS experiments. And with regards to the results, first, I would say that an important outcome are the two prototypes measuring the risk of collision and measuring the social impact. There are major challenges to be addressed with these low maturity prototypes. One example is the threshold, which could be available, could be necessary to impose with regards to safety, to the collision, and also with regards to the social impact. Okay, for me, this is the starting point. We see that it is possible to measure, to determine imbalances, but okay, there are some key challenges in further maturity stages. Then we have the sources of uncertainty. As I have anticipated, the uncertainties are determining some lack of feasibility in the determination of hotspots. And for that reasons, probably we should go to a short-time determination of imbalances in order to impose the measures also at short time. It will not be as today in ATN, in which you have 2 hours to impose regulations and so on. No? We will go to a shorter time frames. And well, finally, the effectiveness of the DCB measures. We tested a set of the DCB measures in order to assess up to which point they could be useful for the drones. And I could say that some of these are very useful for the reduction of the collision risk. No? This is one of the important things. No? We can solve this risk of collisions. But however, this is not the case with the social impact. It's like, okay, we are always focused on reducing the risk of collision, improving safety, but however, we cannot forget that we need measures with regards to the social impact. And well, that's all. These are the points of contact. These are the social media links, and for sure you can visit our stand. Don't hesitate to attend. Thank you very much. And well, maybe I should answer the questions that were raised by Neil. For me, the first one, okay, you have seen that, okay, this is an exploratory research. We have gone into the long term, trying to see how this could work in the future in the urban environments. But I think now we have to go to the short term. No? We have to say, okay, what is mature enough here? And probably we need to reduce the dynamicity of the process. We have proposed something in which you are calculating online the collision risk, the social impact, and so on. Probably in the future we will have some key areas to be measured in the Uspace airspace, and you will have a table with some numbers in order to be able to determine quickly, okay, here you have a problem, without the need of calculating in real time. And this is one point, no? The short term. And for me, the other aspect is the vertiports. You have not seen anything with regards to vertiports. We didn't address this in DACUS, but now we know that this is a resource that will be managed carefully managed in the future, and capacity will need to be taken on board. And that's all. Thank you very much for your attention.
So thank you again. So now we look at the separation minima service. We look at how the capacity could be managed. Now let's take another dimension on the exploratory research, very critical, another question. What would be the common altitude reference? Well, as the Uspace, as we are really talking about VLL, we are really talking about low level of flying. Now, we know also that currently there is no common altitude reference in manned versus unmanned aviation, and even between different drone operators, manufacturers. In manned aviation, we all know that aircraft altitude is determined using the barometric pressure measurements, while drones generally use GNSS. Moreover, barometric altitude estimation is not very accurate in very low level airspace, especially over seas, and cannot address the challenges arising from flying very near or sometimes even lower than ground obstacles. So that is where ICARUS project comes into the game or comes into the play, and really looking to find an answer to this research question. Which technology should be used to measure the altitude and at which UAS is flying, and to which precision and accuracy and integrity? Which reference datum should be used to ensure every airspace user is flying in the same altitude height reference system, and how to determine the vertical distance between two aircraft? These are really fundamental questions. I believe that without that, we cannot move further in the Uspace developments. So that topic, ICARUS, will be presented by Manuel Oneta. I'm looking at him. He's here. Yeah, okay. Manuel Oneta holds a degree of civil engineering from University Politecnica in Madrid. He has 25 years of experience in corporate finance, private equity, and strategic consulting. And since 2010, he has been involved in UAS sector. He has been a business development director for Unmanned Solutions, a Spanish ARPA's manufacturer, co-secretary and chairperson of EuroK Working Group 93 and Live ARPAs from 2012 to 2016. And now he is currently the general manager of Eurus Hispana. So with that, I'm welcoming to Manuel to present ICARUS. Thank you. And your question would be the same.
Okay.
Okay?
Good morning. Okay, so yes, the ICARUS project is a project that its main aim was to answer a seemingly simple question. What should be the common altitude reference, as Neil said, not only between manned and unmanned aviation, but also between different operators in the unmanned world. And yeah, the problem with simple questions in engineering is that usually the simpler the question, the more complex the answer. And this has been the case in ICARUS. Okay, so the consortium in ICARUS, I believe it was a pretty impressive component consortium. We had it was coordinated by IGEOS. Eurocontrol participated. We had a representative of industry, big industry in this case, Telespazio. We had two very innovative drone operators, one Polish and the other Italian. We had the participation of 2 universities, and we have 2 consulting partners, including ourselves, right? And we were representing 3 countries, Spain, Italy, and Poland. So this is the team that we put together to try to answer this seemingly simple question.
In manned aviation, aircraft's altitude is determined using pressure measurement, while drones generally use GNSS. Also, barometric altitude estimation is not very accurate in very low-level airspace, especially over city, and cannot address the challenges arising from flying very near or sometimes even lower than ground obstacles.
The ICARUS solution of these problems is based on the Uspace services. We have developed 2 new services, vertical conversion service and vertical alert service. And have also improved 3 existing services, geospatial information service, GNSS monitoring service, and meteorological service.
International Standard Organization will include these services in the standards related to Uspace traffic management. These standards are strongly recommended to industry and service providers. Thereby, the aviation community will use the results of the project.
We have defined the requirements to fulfill the needs of the drone community and the professional aviation industry, and we had the opportunity to successfully validate our solution in scenarios representative of real use cases in 5 countries.
ICARUS brings a common reference to all the users that share an airspace for increased safety, improving integration of manned and unmanned traffic. ICARUS provides consistent vertical information, resulting in better management of congested airspace and maximization of capacity. The ICARUS Ground Obstacle Alert Service is an enabler for BVLOS operation in very low-level airspaces.
The Common Altitude Reference System proposed by ICARUS is a major element in the integration of unmanned aircraft into the air traffic management system. This exploratory research project points the way towards future work required for designing a robust vertical reference service.
I think that the video explains very well what we have done and the results we have obtained. But in any case, I would like to explain what were the three key objectives that we set up upon ourselves when we started the project. So we wanted to establish, that is the title and the reason of the project, a common reference altitude at very low level airspace, US versus US, and UAS versus manned aviation. But we also wanted to establish a procedure to be able to determine the separation with possible obstacles in the terrain. So all these three objectives are very related, as you can imagine, but they are not exactly the same because the errors that you get in each of these comparisons is completely different, and that's what we have been studying. By the way, I have not said the project already finished in July, so we have the results we have completely terminated, and as I said, those were the objectives. And what are the results? As you have seen in the video, we designed the services that we were going to provide. And something that also was mentioned, but I would like to put an emphasis, is that these services that we have defined are already in an international standard. So what this means is that, and they were published the month that the project ended, which is something quite unusual. What this means is that the future Uspace service providers should implement the ICARUS services, okay? So to answer your question, what should be done? Okay, we have defined services that need to be implemented, but now we need to provide an implementation for that services. And I think that it is something that we have raised this problem, that Uspace service providers should provide some services, but we don't have those services finalized. We have prototypes, we have a proof of concept, we know that they work, but now you have to solve all the problems that are required to pass from a prototype to a operating commercial service. So that would be my answer.
Indeed, this was really one of the excellent projects with very concrete results. Now looking for the, going further maturity, but more on the implementation direction. So this is something to be underlined. Let me come to the next project. It is USEPE. USEPE actually, they said it is not enough, what Bubbles has researched. We would like to look at the separation management from another angle. And they come with a completely new, what we were discussing during the CONOPS workshop is, it was said like new and bold concept called D2 to C2. To answer that question. So they have been really looking at what will be the predetermined separator, drones themselves or the Uspace service provider or Uspace systems. Well, they have been really trying to answer that research question, and that would be presented by Esther Nistal-Cabana from USEPE. She's the project coordinator, and she has a master's degree in aeronautical engineering in Madrid, Polytechnic University. She specialized in aeronautical air navigation. She has more than 23 years of experience working in state-owned non-profit organization in ISDF. She worked in several ATM EC-funded projects, among which we can say approved SAFE, Leonardo. And recently, she has resumed to the European-funded activities and worked in InverCard and PG-13 ERICA projects as a contributor. And finally, as I said, she's the project coordinator of USEPE. So floor is yours, Esther, please. Thank you.
Hello, good morning. Happy to be here. USEPE stands for USpace Separation in Europe. It sounds Italian, but we don't have any Italian partners this time. We, unlike other projects, we only have had 24 months to accomplish all the activities, so we have done our best with the time given. We are about to finish in 2 weeks' time. We will have our final maturity gate with Neil, but we already have the results that I can share with you, okay? So, okay, this is the consortium. We are 7 partners from 4 different countries, Spain, Germany, Norway, and Belgium. I think we have the partners combination covers the necessary knowledge to accomplish this project. We have system engineering companies, experts in artificial intelligence, big research centers, and experts in big data. So you see the partners on the screen, just 7, and not too complex, the consortium to handle, okay? We also have one partner, it's the exotic partner. It is called Police, and they represent the cities and the region's interest, because we think the cities play a major role in the USpace implementation. Okay? And also we have the University of Hanover. Let me mention that because in this project we have taken very seriously into consideration the wind data. We have simulated extensively the wind data. Okay? Our main goal was to find a separation method for the drones in the urban areas. And unlike other projects, we didn't know the solution. We knew the problem from the scratch, from the very beginning, but not the solution. So we have taken into consideration stakeholders' views. We conducted a survey to gather their needs. We held an initial workshop. We transformed their needs into requirements, and then we did a huge study, literature review, about existing separation methods. We end up with 13 different separation methods. We narrowed down the list just to 4, and we apply the analytic hierarchy process just to have one separation method. It's a combination of methods, to be honest. That would be our main goal, to find this solution, develop the solution with the help of the stakeholders, and to validate the solution using fast-time simulation. We had other objectives in mind, the use of artificial intelligence and machine learning algorithms, and also, as I said, to include the wind data into our concept in our simulations. The wind data is really, really important in this project because for all aircraft operations, the wind is important, but for drones, they are so small that are so sensitive to any wind fluctuation, okay? This is our solution. A new airspace structure. The 3 pillars. We have segments. They are not segments, really. They are portions of airspace. They are volumes. We have corridors, fixed corridors. The segments can be adapted and changed, can be split, merged, can be closed, for example, due to wind conditions, due to prioritized flights, or due to restricted areas in the city. So as I said, we have segments, portions of airspace that we adapt. We have the corridors, and we also have geovectoring rules to accommodate the speed, the rate of climb, the rate of descent, and also the heading of the drones. Okay, those would be our the 3 pillars of our concept. Here you have, okay? So this is completely new. It's a new airspace structure. That was our main achievement, but we also have other achievements along the way. We have done a lot of things to obtain a tactical deconfliction algorithm using safety volumes, as other projects have done before. We have used the machine learning algorithm to enhance the strategic and tactical deconfliction to reduce the computational time. We have used the accurate wind data for the city of Hanover. And we have gathered an unexpected achievement. We didn't plan to use the Blue Sky open source simulator. We had to use it due to some internal problems. And we have sent back to the research community a plugin called USEPE plugin. It's publicly available. Everybody can use it. It's in our website and also in Blue Sky website. Results. We have simulated 3 different use cases: last mile delivery, emergency situations, and urban surveillance. And the results have been really good for low and medium density, background density, but to be honest, for the very high density of background traffic, the results are not so good or not as good as expected. So this leads me to the question you were asking, Neil, about the future work. We think the dynamic updating of the segments must be enhanced with the use of machine learning. We have used 4 different parameters to dynamically update the segments, and we think 4 parameters only are not enough. And we need to use the machine learning to help us with this, because otherwise we couldn't handle very high densities in this urban environment. And here, the contact details. In our website, you have the machine learning plugin available for all of you. And we have been also very active in LinkedIn.
I think exceptionally this time, timing-wise, we are doing very well. So far we have been really talking about more defining operational concept from the separation management, from the capacity management, etc., common altitude reference. Now we will change a little bit the perspective and looking on the enabling technologies with the FACT project, which stands for Feature All Aviation CNS Technology. And that project will be working on the update of the CNS technology, bridging the future Uspace services with the conventional ATM systems, and researching on the feasibility of the performance-based ICNS concept. That would be presented by Petr Kasek. Peter is working in Honeywell Advanced Technology Europe in Czech Republic since 2005, currently as lead research and development scientist and a system architect. Most of his career he focused on surveillance systems such as traffic collision avoidance, DACUS, DAA, detect and avoid, and ADSP applications, and being involved in multiple SESAR projects since SESAR 1. He holds PhD degree in physics. And he is as well the project coordinator of the FACT project, and he will tell us all about in 7 minutes. And I forgot, your question would be, you know, what would be the immediate thing that if you want to implement what you have, let's forget about the maturities at the moment. What do you think is needed to make this reality the most? Okay. Thank you.
I tried. Thank you for the introduction. Hello, everybody. So, as stated, I am the project coordinator of the project FACT. The project is ending in December, so we are just now concluding the results. Let me start with the introduction of the project team. So, the project brings together the industry, represented by Honeywell for the aviation technologies and Nokia for the telecommunication technologies. 2 universities in Istanbul, technical universities in Istanbul and Eskişehir, addressing respectively drones and ATC perspective in the project. 2 representatives of airspace users, General Aviation Pilot Association, AOPA in Germany, and SARPER, which is air taxi provider in Eskişehir Airport. And Eurocontrol was focused mostly on the spectrum aspects and also coordinating of the project activity with the related projects and community. So, as stated, project focus on evaluating how we can integrate really cellular network technology into the performance-based CNS concept, communication, navigation, surveillance concept. So especially within the Uspace community, cellular network is quite often referenced like one of the main candidate technology for identification for different type of application. It is natural to look if we go now and try to implement the application based on this technology, what it really means. FACT project did not focus only on the Uspace users, but looking forward, saying these users will need sooner or later share the airspace with the general aviation, helicopters, and these users also have very varying CNS capabilities. So how we can somehow make the capabilities of all these users interoperable and being able to work together, so really we can gradually remove the segregation and let them to operate within the same airspace smoothly. So when speaking about the using of the cellular network technology, the key motivation is probably infrastructure exists, and also due to a lot of components available on the market, affordability of such type of system. So far it sounds very good. Where are the problems? Of course, if we want to reuse the existing infrastructure, it is designed for the terrestrial users. They are not optimized for the aerial use. So it brings clearly the limitations that needs to be somehow handled on the operational design. And the second, these networks are not built for the safety critical application. So you do not have the guarantee minimum quality of service. So you cannot guarantee that at some point you will not have degraded performance, and your operations need to be able to handle such situation. So these are the two main limitations of the existing network. So then we hear quite a lot about the 5G and new releases of the 5G specification, which include many features that aviation from a long time is asking for. Ultra reliable connection, low latency, localization, including millimeter wave. It is in the specification. Is it deployed somewhere in the world, really? No. These are the features which are for the moment on the specification, but as the operator do not see the business case for them, they are not deployed in real world. So there is definitely the opportunity. However, there is something that needs to happen before we could really use this technology. So this somehow formed the two streams of the project activities. We focus in one side on looking how we could use the existing public networks without modifying them, because based on the discussion with the network operator, motivate them to change the configuration of the existing public networks. It is a huge investment. They do not see the value. We are speaking about thousands or tens of thousands users with respect to millions that they serve each day on the ground. So it's not so interesting for them. So one thing, okay, if we want to reuse the cellular network, how we can do it with the limitations that are there. The second, if we want to benefit from the 5G capabilities, again, then it requires the investment, but are we able to combine the use cases and build the business case so that it makes sense to build such type of network really for the aviation? So, considering the project activity, saying the practical evaluations and technical activities were focused mostly on the use of the public network, both in 4G and 5G. So really looking on the limitations that we observe and formulating the recommendation how we could incorporate it in the design of the operations. And then kind of looking on the use cases that would make sense really for the 5G, probably dedicated networks that could really serve like safety critical application and highly performing CNS applications. So technical evaluations, from the logic that I described, we focus really what we can do on the vehicle or user side without really touching the network. So how we can biggest problem is interference when you are increasing the altitude. You will have the interference from different base stations of the network, and you have also the frequent handover between the base stations. So these are two aspects that we try to mitigate through the directional antennas, through the different kind of technical means. So this was a part of the activities. We also look whether some of the positioning capabilities which are already present in the public networks could be used, for instance, like the kind of detection of the maybe GNSS spoofing. So this was another part of the work. Then we also looked whether the potential degradation of the network are typically stable, or can we know them in advance, or are they predictable, or they happen really in the way that we cannot expect them, and we need to be able to handle them really in the tactical way. So these were kind of technical evaluation, and then to have a bit more fun, we make also the operational demo. So we built the whole kind of ecosystems at Eskişehir Airport, where we installed the experimental CNS device on helicopter, on Cessna, on 2 drones. We put them all in the air. We enabled the traffic situation awareness application. So all these vehicles reported their position on the ground. We had on the ground the server, provided Uspace service traffic information. So we collected the information, we created the traffic picture, and we disseminated this traffic picture. We sent it to all the vehicles through the direct links, and we sent them also to the ATC tower and to the remote pilot. So everybody has the same traffic picture. We measured the latencies, we measured the message, how many messages was lost, and all these kind of technical parameters. Beyond this, we also implemented the alerting service. So for the drones who fly automatically, we know also the trajectory. So we also monitor if they do not deviate from the trajectory, and in case the conformance alert, we alerted the relevant users. So this was the second type of service. Again, different type of communication for measuring latency and these parameters. This is just to show how our architecture looked like. I will not go in the details. For more details, I recommend if you visit us on the stand in the lobby, and we can provide more details. So now answering your question, and I apologize if I'm a bit long. So what can be done immediately? Our recommendation for the use of the public networks today, our suggestion, most of or nearly all the degradation that we saw are stable and known in advance. So we recommend when the airspace or Uspace is designed and claimed by the member state, create the available coverage maps in different altitudes. So you know in this particular airspace what are the limits up to which in the altitude the coverage of the public cellular network is sufficiently stable. And based on this, you can allow the operation. So until this altitude, if you have the cellular network device, we allow you to do these operations. We can reduce the separation, etc. Beyond this, having kind of monitoring service, which in case there is a really kind of degradation or outage of the network, have the alerting mechanisms and have the procedures in place how to handle such situation. So this is, I think, it can bring the value. There are limitations. We need to live with these limitations, but from our results, it is possible to incorporate them in the operation definition. And the second recommendation is for the dedicated network. We need to bring the stakeholders together and think how to build the business case for the network providers and ground industry, under which condition it could make sense. It would make sense for them to build maybe the dedicated network around the vertiports, around the airports, where the CNS requirements are high. Because 5G has the possibility to be navigation augmentation system, communication systems enabling the surveillance, so it can serve multiple use cases. But we need to build the business case in order that it can happen. Thank you.
Thank you for the recommendations.
I apologize if I'm wrong.
You are very well. So thank you again, and for these very good, important recommendations. I hope that you are coping with the speed. We are in the last 2 projects, but before maybe going ahead, maybe just step back a little bit. I mean, if there is one thing left in your mind, maybe I have an invitation, a question for you. After all this presentation, what would that be? What is the most important thing which is kept in you until now? I would like to invite you to think about it and take maybe a deep breath before we continue, because I know that we are bombarding you with a lot of information and it's not easy to digest, and as well as inviting you to the exhibition hall so that you can zoom into the projects if you are interested to get more. With that, let me continue with the Aspirate project, which stands for Airport System Protection from Intruding Drones. We cannot forget airports, could we, when we talk about ecosystem of the ATM or Uspace. So that is the project which is looking, another SESAR exploratory research project which looked after that, and trying to answer the question of how to deal with the problem of protecting airport operations, particularly from unauthorized drone intrusions. And that's what the project is about. Now, please join me to invite Pablo Lopez Loches from Aspirate to explain you all about in 7 minutes again. And he is currently head of Technological Surveillance and Innovation Financing Department at IANA. He has worked in the company for more than 6 years in the Innovation and Customer Experience unit, participating in digital transformation, customer centricity and sustainable developments at IANA airports. And he is being in charge of drone and UAM programs, among many others. Stage is yours.
Hello, everyone, and thank you very much, Neil, for the introduction, and all of you for attending this session. I'm going to present Aspirate project. As Neil said, this project is about how to protect airport operations from unauthorized drone intrusions that we have in our airports. So in this slide, you have an introduction of the project. Aspirate means Airport System Protection from Intruding Drones. The name of the project says the main objective of it. And in this project, 7 companies have participated in the consortium from 3 different countries. From Spain, we have INTA as the project coordinator, Enaire and AENA. From France, we have Onera. And from Italy, we have Aliscar, Cira Institute, and Solsower. This project started 2 years ago, and today it's a sad day because it's the last day of the project, so we are going to say goodbye to it. But I'm sure that we will use the results obtained in the project for future ones. Here you can see the main objectives of this project. The first one is to get awareness of airport operation scenario degradation due to drone intrusions. The second one is to define a service-oriented operational concept, system architecture, supported by procedures and regulation to manage both airport intrusion and airport operations efficiently. The third one is to validate the operational concept and system architecture according to performance objectives. And the last one is to set recommendations for future regulation applicable to the protection of airports from drones. Here in the image of the right, you can see the system high-level overview that has been designed for this project. Here we had taken into account different threat levels, different technological levels, know-how levels, and the user's interface level. And in the bottom image, you can see the operational concept with 2 main points. One is the definition with a decision-making tree for the stakeholders involved in this process. Here we have to take into account the protocols of when we detect unauthorized drones in the airport or close to the airport. And also we have identified different zones and different risks inside the infrastructure that I'm going to explain you in more detail now. So this is an example of the layout concept of the project. Here you can see, for instance, different circles with the drone detections range of the sensors we have considered for the project. You can see also we have defined the airport boundary, the critical elements of the airport, and also the safety radio levels of these critical elements with different colors from green to red. And also you can see how we have applied over this draw the countermeasure units and the range of these units. Here, this is the operational concept that we have designed, and we have applied this in a simulation, in a simulator tool that we have designed in the project. Here on the bottom, you can see a screenshot of this tool. So we have been able to apply all these criteria designed in the project to a real scenario. In this case, is the airport of Milan. So we have introduced the maps of Milan airport in the simulation tool. We have applied over it these criteria defined, and we have made different simulations in which air traffic controllers, people from the airport, law enforcement agencies have participated in order to validate this tool and to test how will be the procedures. You have here a list of the main results of the project. One of them is the methodological framework, the requirements for this hybrid system, the operational concept and architecture, the human interface, the human-machine interface of the project, the validation platform. I think this is one of the main ones because here you can see the feedback of all the stakeholders involved, and it's a really accurate tool to deploy for airports and for navigation system providers. We have done here the validation results, the new roles and responsibilities for all the stakeholders involved, and the lessons learned and the obstacles and recommendations. In this project, we have taken a lot of material that is confidential. It involves a lot of safety and security procedures for airports. So not all the deliverables of the project are public, but here you can see the ones which are public and which has a really good summary of the project. One is the summary of the scenarios assessment. The other one is the summary of operational concept and architecture definition. The other one is the demo software for validation, the summary of validation results, and the last one is a white paper on recommendations for future regulations. All of this material in our webpage. If you scan this QR, you can access directly to our webpage. You can follow us also on Twitter. And if you have any doubts, you can write us to this email, or if you want to know more info about the project, or you can talk with us during the breakfast later. Well, that's all from my side. And answering your question, I think that from the airport point of view, at least, the needs for future research and development projects we'll have to take into account how to integrate drones and UAM operations in the airport environment. We have to make compatible both operations of drones and UAM to the current operations of the airport. We have to try to test also autonomous operations from our side, from the airport. It really makes sense to test different use cases with drones, for instance, in an autonomous way, not piloted by someone. So we have to drive in that direction. And also, I think it's important to mention something that I have been talking with some colleagues here before, to take into account all the results and all the projects that we are presenting today for future projects, because they are a really good basis for future consortiums that can make something similar and not to repeat work done, because sometimes with these projects we start doing something that is already done in other projects. So the dissemination process is really important, and I think it's really important to take into account all these projects that we are presenting today here. Thank you very much. Thank you.
And finally, last but not least, we have left with Metropolis II, not yet presented yet. And they are also an exploratory research project, obviously, but addressing a similar problem from another angle. They have been asking themselves in their research what degree of centralization is required to manage to use space operations. And they have really looked at 3 scenarios from centralized, decentralized, and hybrid model. And here today, Andrea Badia is here to present Metropolis II and their findings. It was a very exciting project, I must say, with very, well, results are a little bit not in line with the expectations, but you will find out when he's presenting the results of the project. So Andrea is from Romania. He moved to Netherlands to pursue his BSc and master degree in aerospace engineering at the Delft. He then became a PhD candidate at Delft at the end of 2020, which he started working on the Metropolis II projects. I have witnessed that he ran very fast during the demo, so I hope that he will be running fast in his presentation as well, so that he can fit into 7 minutes. And the question for Andreas is the same. Now that you have already concluded your TRL2 gate, well, we also know that there is still, although there is a concept behind, there is still some study. It is not yet ready for TRL2. So I would like to invite you to speak a little bit on this, what is really needed to bring this to the next level. Please welcome.
Thank you, everybody. Okay, so hello, everybody. Today I'll present really shortly our work in the past 2 years, the Metropolis II project. During Metropolis I, some of you might know that my colleagues that did that project looked into the airspace structure and what exactly is the best airspace structure for an urban environment. And that was the layers concept. And within the Metropolis II project, we wanted to take it further and actually determine what is the best way to control traffic in urban airspace. We assembled a team from all around Europe, 3 universities, TU Delft, Linköping University, and the University of Patras from Greece, and also partners from industry, NLR from the Netherlands, Unifly from Belgium, ENAC from France, and Everest, in the meantime, turned to entity data from Spain. We wanted to investigate how exactly we should control aircraft in urban airspace. Should we turn towards classical air traffic control, where a central authority commands aircraft around, performs the separation mostly strategically, or should we look in a more decentralized approach, such as how we approach car traffic, where you just go in your car in the morning and then just deconflict your way to work, for example? Or should there be a combination of the two, a hybrid concept, where we perform both strategic and tactical separation at the same time? To do this, we looked into developing traffic scenarios based on the city of Vienna, and then we set up to simulate millions of drones in order to answer this question. We also looked into uncertainties, so we included a simplified wind model, or what happens if some drones don't follow the rules, and so on. We assessed the performance of the 3 concepts that we created in function of several key performance areas, such as efficiency, safety, equity and access towards airspace services, and so on. And then, we simulated, and we made fast time simulations, and even a demonstration, a live demonstration, to test this out. In a long story short, one graph that summarizes the whole project, you have it over there in the corner. I won't explain it now, because it's just a graph, but I'll be happy to explain it at our stand. However, in terms of safety, we have discovered that the degree in centralization is not the only major contributor to safety in airspace. While we did determine that the hybrid approach is the best because it combines both the strategic advantages of spreading traffic out and preemptively eliminating hotspots in the airspace, and also tactical separation, which can account for the uncertainties and the quirks of a central authority and of a centralized system. However, we also determined that the airspace structure still has great potential for improvement and determined a lot of the safety factor in all of this. In terms of efficiency, of course, we have discovered that planning in a decentral way is more efficient overall, as agents will follow their shortest path to their destination. However, if you try to increase safety by including a strategic separation, then you inevitably have to trade off efficiency. And then lastly, in terms of equity, this also needs to be taken into account when designing a control environment and also a hybrid system, as especially if you use delay as a separation mechanism, then you might tend to inequitably delay certain agents, and that is not equal for all the stakeholders within the Uspace environment. So yeah, for more information, you can contact the project manager, Joost Ellebroek, or you can come to our stand, and we'll be happy to talk to you about Metropolis II. Thank you. Oh yes, and I forgot to address the question. So what comes next? Well, there is still lots to do. We have looked at these concepts in a more scientific way, an explorational way. There is still the operations itself, how stakeholders interact, who does what, if the drones should actually perform tactical separation on board, on themselves, independently, or should they, for example, also do it centrally somewhere and simply receive commands. These questions are open, and hopefully we'll see a Metropolis III to answer this. Thank you.
So there we are at the end. I would like to have one concluding remark, with your permission. Now, you have seen 7 individual projects. They have been all working on different aspects of a very fundamental but very same question. You may wonder how those come into the big picture together. So there I would like to mention that we also have a ICARUS XUIM project under the lead of Eurocontrol, thanks to our colleagues. They are here, Andrew and Ludo. They have been really leading this, the CONOPS aspect, where all the individual results coming out of these exploratory research projects, also as well as the VLD projects, they try to keep the big picture and to see how those projects have contributed to the CONOPS. Did they come with the new service definitions and proposals? Are they aligned with the CONOPS, etc.? So this is something important to mention, also to thank to our colleagues for their effort on this. With that, I would like to conclude that session first to thank all the speakers and also respecting the timelines that they're slot. And I also especially would like to thank all the audiences and paying attention.